Okay, thank you very. Hope you all had a good weekend, and welcome back to Heat Transfer. Uh, we will continue from where we left off. Okay, we had started discussing about the directional properties in radiation heat transfer. We started when we started, we were defining terms like total hemispherical emissive power, total integrated overall wavelengths, and we had kind of handled that problem. We also defined what is called monochromatic emissive power, which is emissive power at a particular wavelength, which when integrated over the entire range gives you the total emissive power. Okay. The hemispherical at that point we had said hemispherical at that point we had said was the term meant that it is integrated across or over all directions, right? And therefore, uh, how do we define or how do we like we had monochromatic emissive power? What is it that we can define? What is that parameter that we can define to capture the directional functionality or directional dependence of this emitted radiation, right? So that is our goal. Now, in order to do that, what we did was we defined something called solid angle, which is more of a geometrical concept, and we did that. Now, what we will do is we will define a second term called radiation intensity. Okay, so let me start sharing my screen. I believe you can see my screen now. Okay, so this is what we had done last time. As you can see, we had defined what is called the solid angle, and we had also said that if you take a sphere and take an infinitesimal area in a sphere, then the solid angle subtended by that infinitesimal area at the center is sine psi d psi d phi, where phi is the azimuthal angle and psi is the zenith angle. Just give me a minute. My OneNote is behaving a little weirdly in the sense. Yeah. Woken up. So this is the zenith angle, which is from the vertical line, and azimuth is along the circumference. Okay. So sine psi d phi. Okay. So the next term that we are going to define is called, very important term, is called the radiation intensity. So what does that mean? It means that the total intensity of radiation, again the word total when it comes to radiation heat transfer, means that it is summed up over all wavelengths. Okay, so keep that in mind. Total is not what we use in colloquial terms or total is. So uh, the word total has a technical meaning here. The total intensity of radiation, and we are going to define it as I, small I. Okay, is the radiant flux, which means per unit area. Okay, is a radiant flux passing in a specified direction per unit solid angle. Okay, what do I mean by this? Okay, let us try to first look at what I what I'm saying. If this is a surface and I take a point somewhere here, okay, so this infinitesimal area dA, let us say, on the surface is going to emit radiation in all directions, right? I mean, most normal surfaces, we will define such a thing called diffuse surface. Unless the surface is polished and supposed to have certain directional properties. Otherwise, any surface is going to emit radiation in all directions. Now, if I want to find out what is the radiation I at a certain in a certain direction, what I will do is I will define a solid angle d omega, okay, and write it as I is dE d omega. E, remember, emissive power, or the total hemispherical emissive power. Or what it means is E therefore is integral I d omega, where the integration is carried over in all directions encompassed by a hemisphere. Okay, so let us write down what we just drew. So consider, I'm going a little slow here because this is the important concept to grasp. Okay, so consider a surface emitting radiation. Okay, we wish to find the intensity of radiation in a direction shown by this arrow. Okay, we wish to find I. Okay, so what we'll do is let us draw an imaginary solid angle and say that the radiant flux passing through that is E, dE, sorry. Okay, so then I will define I is dE d omega. Or I can write as we have defined here also, it is that quantity which when integrated over all directions gives us the emissive power of the surface. Okay, and once again that word total means summed up over all wavelengths. Any questions? Or before that, let me complete this. If I is E d omega, then I can write that E is going to be what? Is the integral. The integral I'll put later. The limits I'll put later. I'll first write I. And what was the d omega? Sine psi d psi d phi. Okay. Now I have to integrate over the entire, in all directions along the hemisphere. So to capture a hemisphere, remember psi is the zenith angle. So think about it. Psi is the zenith angle. So that can go from 0 to 90. And phi being the azimuth can go from 0 to 2 pi or 360. It's like this, right? This is my, let us say this is the unit radius or so, 0 to 90. And then, so you get some kind of a quarter circle. And then you rotate it for the 360 degrees. You find that you get a hemisphere, right? So once again, this, then this whole, whatever this quarter circle, now rotates 360 degrees. So therefore, the limit of psi is 0 to pi by 2. The limit of phi is 0 to 2 pi. So let us write that down. Psi is 0 pi by 2 and phi is 0 pi. Okay. All right. Let me stop here and ask you any questions. I know this is a little imagine. You have to be a little imaginative, but slowly I think you will get it. If something is coming, okay, in a certain angle, solid angle, and of course the solid angle consists of two parts. You break it up into planar ones, azimuth and zenith, and then you integrate it in all directions. Okay. Yes. Questions.
So can you please explain the limits of psi and phi once again?
Okay. Let us go back to this picture. So how do you get a hemisphere? If I have a normal, let us say like a pen, can you see me? Or very small, right? So maybe if I stop sharing the screen for a while. Okay, now maybe you can see me, right? So let us consider this pen, for example. Now, this is at 0, the zenith angle. I rotate it from the vertical to the horizontal direction. So I'm going from 0 to 90 degrees or pi by 2. Clear? So by doing that, what have I got? I've got a quarter circle, right? You take the entire area through which this pen traverses, covers during this travel from 0 to 90. It is a quarter circle. Now you take this quarter circle and rotate it for 360 degrees. So then that creates a hemisphere. Okay. So that's why the zenith angle limit is 0 to 90. The azimuth angle limit is 0 to 2 pi or 360. Is that clear?
Yes, sir. Thank you, sir.
Okay. All right. Let me get back to the sharing again. Any other questions? Yeah, this needs a little bit of visualization. And to be honest, even I am also not very good with 3D visualization. Okay, I hated engineering drawing. At that time, we didn't have AutoCAD or anything. It was all about graph paper, sorry, drawing paper. And I don't know if you have ever seen this. There is this tool called Drafter. Even before that, there was something called a T-scale. If your parents have been engineers, they would have used a T-scale. My father used a T-scale. Okay, then we use something called Drafter. Of course, now at our times, AutoCAD was just coming up. Now, or CAD was just coming up. All right, so this is what it is. Okay, this is now the question is okay. So how do I know what is I? If you give me a psi and give me a phi, how do I know even what is I? Right? What is the intensity in a given direction? That's the question. And what about the directional dependence? I'll draw the surface again and say, and I'll draw two directions. Okay. One which is normal to the surface, and I'll call that IN. One which is at an angle. Okay. One which is at a zenith angle psi from the normal. I'll call it I. Okay. So here we are thankful to a friend called Lambert. So again, this is not universal. So I'm writing for many surfaces. Okay. I is IN cos psi. Okay. This is called the Lambert's law. Okay. So for many surfaces, what do we mean? That's vague. Okay. So I would say such a surface is called a diffuse surface. So many real surfaces, I would say most real surfaces exhibit this behavior. Okay. Where the emission happens in all directions in a diffuse manner. It's not the same in all directions. Of course, and as Lambert's law says, that for a diffuse surface, the intensity of radiation, radiation intensity in the normal direction is the highest, and it goes down as as you go to a certain zenith angle. Okay, so keep this in mind. This is a diffuse surface. So if you substituting Lambert's law, what we get? You look at this equation for E, or expression for E, and put I as IN cos psi. E is integral, double integral, IN cos psi, sin psi, d psi, d phi, where psi goes from 0 to pi by 2, phi goes from 0 to 2 pi. Okay. Acha, quickly, someone, please do this integration and tell me what do you get. Okay. While I sip my cup of chai, please do this integration and tell me what you're getting. Take IN out. You don't know what is IN. But otherwise, sin psi cos psi is what? Sin 2 psi by 2. So what are you getting?
Pi into In.
Exactly. Wonderful. If you do this integration, you get pi In. Okay. Please keep in mind that this is only if surface is diffuse. Okay. Let us do a quick problem here. The problem is, again, let us draw surface. Assume surface is diffuse. And epsilon equals to 0.08. Emissivity is 0.08. Calculate A In. The surface is at, sorry, I should write, surface is at 300 feet, more or less room temperature. And B, calculate the radiant flux emitted within the cone uh, and whether it's let us make it 0 to 60. So let us see, how do I get In? How will you get the intensity of radiation in the normal direction?
We can calculate E using Planck's law and then we can use the above formula to get In.
Not Planck's law, Stefan Boltzmann law. Okay? E is given by Stefan Boltzmann.
Okay, so yes, sir.
Epsilon EB, so definitely 0.08 times sigma T to the power 4. Okay, so you will get it. Okay, I'm not. So therefore, In would be E by pi. Okay, what would be the unit of In? Watt. Remember dE d omega. Watt per meter squared steradian. So whatever you get, that's your answer. Please keep that in mind. Okay. Next one is calculate the radiant flux emitted within the cone defined by that. Okay. If the psi extended from 0 to 90 degrees, it would have been just E. Okay. But what they're saying is no, it is the radiant flux emitted in the cone 0 to 60 degrees. Okay. So that radiant flux emitted within the cone will be equal to, it's simple, only thing that will change is are the limits. in cos psi sin psi d psi d phi. The phi limit stays 0 to 2 pi, but the psi limit changes from 0 to 60 degrees. Okay. Please work this out. So essentially what we said is, what we are calculating is, this is my surface is going to emit in all directions. I wanted to know what is it that it emits in this cone. Okay, all right. One last concept that we are going to talk about. All this while, we have still, you may be thinking that what's in conduction, we started by saying that this is the amount of heat that is going to be transferred. Started from Q. Here we have not even gotten into Q. We are still talking about what is emitted, what is absorbed, okay, what is reflected, all that. So we are all equipping ourselves. We are getting equipped with the different tools, which will now help us calculate the heat exchange between two surfaces. Okay. We are not done yet. There is one last tool in your toolbox that you need. That is called Kirchhoff's law. I'm not sure if this is the same Kirchhoff whose law you use for solving electrical circuits, but most likely it's the same person. Okay. Because as I said, people in those days were truly brilliant. These days we use the word brilliant very loosely. Okay. But truly brilliant guys existed in those days where they made pioneering contributions in multiple fields. Okay. Okay. What the Kirchhoff's law says is the monochromatic. Essentially, you know what is Kirchhoff's law. Okay. Without knowing that it was Kirchhoff who first showed it, which is that emissivity equals to absorptivity. But actually, the Kirchhoff's law definition is this: the monochromatic emissivity of a surface is equal to its monochromatic absorptivity. Okay. The last part is important. If the surface emits in a diffuse manner. So this is true only for diffuse surfaces. Friends, please keep this in mind. It is not universal. The other point to note is what Kirchhoff said. Monochromatic emissivity is equal to the monochromatic absorptivity at a particular wavelength. Okay. So what is Kirchhoff's law saying? Kirchhoff's law is saying that for a diffuse surface, epsilon lambda is alpha lambda. This is very important. Why? Because very important law. because this is the first time something is relating the emission characteristics to the absorption characteristics. Okay. Now, how did we define a gray surface? Gray surface, we said that gray surface is one where we can neglect the variation of emissivity with wavelength and take a mean value and apply it across all wavelengths. So therefore, for a gray surface, it means epsilon equals to alpha for a gray surface. Okay. So therefore, this law, this one, okay, the average absorptivity is equal to emissivity. This is valid for what? This is valid for a diffuse and gray surface. Please note, I can write epsilon equals to alpha if it is diffuse and gray. I can write epsilon lambda equals to alpha lambda for a particular wavelength if it is diffuse. Okay. Now, for most practical surfaces, we'll assume them to be diffuse and gray, real surfaces that we encounter around us. Yeah, specialized surfaces, they're made specially to have some characteristics, either emission or absorption. That's different. Okay. Otherwise, unless otherwise stated, we are going to assume, we will normally assume a real surface to be diffuse and gray. Please make a note. I'm not writing it, but please make a note. All right. So with this, we are now ready. Okay. Finally, the moment has come. We are now ready or equipped to calculate heat transfer between two surfaces. Of course, when I say heat transfer, it's heat transfer by radiation. Okay. So let us start with heat transfer between two black surfaces. We'll first do black and then go to gray or real surface. Sorry, yeah, black surfaces, and then go to gray surfaces. To start with, let us assume the exchange between, let us say I have two surfaces, okay, maybe this book and this book at a certain angle to each other. This fellow is also radiating and absorbing. This fellow is also radiating and absorbing. And to start with, both are black surfaces, but at different temperatures. So, what would be the net heat exchange between these two surfaces? So, let us first take two small elements. Okay, the first one, I'll denote it as a okay. So this I'll call dA1. This is at a temperature of T1. Okay, and somewhere I'll draw something called I'll name this BA2, and it is at a temperature T2. Okay, so let us say that from this point to this point, very bad at drawing lines. Let me see. चलो भाई इसी से काम चलाना पड़ेगा. Okay, so and this distance is separated by distance L. Okay, let us draw the normal. So this is the normal to the surface dA1. Let us say this angle is beta 1. And similarly, this is a normal over here. Let us say this angle is beta 2. Okay, you understand this? These are the two surfaces. If I take two small areas on each of these surfaces and try to see how they are aligned and what is the space between them, the distance between them, this is what it is. Okay, so let us leave it at this and write what we just said. Let us consider two elemental dA1 and dA2. Okay, and I want to calculate net radiation. Okay, because see both of them will radiate, and part of the radiation emitted by both of them will reach the other surface. Okay, and when it reaches the other surface, because it's black, it is going to be absorbed. Okay, so both surfaces will absorb radiation, both surfaces will emit radiation from each other and to each other. So what is the net? How much is, who is receiving more and who is emitting more? That we have to calculate. Of course, that's going to depend on T1 and T2. So calculate net radiation heat exchange. Between dA1 and dA2. Okay. So let us, friends, let us go step by step here. One. Intensity of radiation I emitted by dA1 at dA2. Oh, sorry. Let us do first the other one. dA2 at dA1. It is being emitted by A2 and coming to A1. What can I write? This is equal to dA2 cos beta 2. Why? Because this is the area, projected area of A2, which is normal to L, the line L, right? Or line of length L. Or it is again, what you can say, it is the IN is the normal. Okay, no, sorry. I'll come to this later. I mean, let me take step by step again. Okay. So this I was talking about this. Uh, First, let us write very simple thing: IN cos beta 1, and this would be what E. Straight लिख लेते हैं. Now that you know, I can write that IN was E by pi, so sigma E1 to the power 4 by pi cos beta 1. Okay, I leave this now here. And then let us take the solid angle d omega subtended by dA2 at dA1. That is going to be equal to dA2 cos beta 2 divided by L square. Okay, dA2 cos beta 2. If you, because at an angle dA2, if you want to take the projection normal to the length, the line L, so that is dA2 cos beta 2 times what was solid angle? Solid angle is the angle numerically equal. Remember that numerically equal to the area which is covered by a unit sphere if you draw it around that. So therefore divided by L square. Clear? So now therefore rate at which radiation emitted by dA1. Okay, what did I write? Intensity of emission? No, I wrote it wrongly. Please correct this. This is dA1 at dA. Sorry, sometimes while writing it gets a little confusing. Pardon me for that. Is emitted by dA1 in the direction of dA2, intensity of radiation. I think that's what I should write, not at dA2. That is probably more correct. The direction of dA2. Okay. This is technically better. So emitted by D. So therefore, and then the solid angle we have written fine. Radiation by dA1 flows towards dA2. What would that be? I d omega dA1. Because the intensity of radiation in the direction of A2 is I d omega. In the area, I'm trying to find out the total radiation. So that has to be multiplied by the area dA1. So Q. So now put it, I figured out what is I, what is d omega. So I was sigma E1 to the power 4 divided by pi cos beta 1 and d omega cos beta 1 and d omega would be dA2 cos beta 2 by L squared dA1. Okay, so what we will do is we will group it a little differently and write it as cos beta 1 cos beta 2 dA2 together by pi L squared, then sigma d1 to the power 4 dA1. Okay, so this term we'll define it by something. We'll call it d capital F 1 to 2 sigma d1 to the power 4 d1. So this is what is emitted, radiation emitted by dA1 that goes towards dA2. And keep in mind that all this is absorbed by dA2 since it is a black surface. Yeah. So I will just complete this lecture by defining what is dF12. This is one of the biggest, most significant concepts of radiation exchange. This friend is known as the shape factor. Okay, or view factor. These are the most common terms. Some people use configuration coefficient, some people use angle factor, but those are not very widely used. Okay. Shape factor of dA1 with respect to dA2. What is it saying? If you look at this, sigma T1 to the power 4 dA1 is what? The total energy, rate of energy, radiant energy emitted by dA1, right? And this dF12 is fraction of that energy that reaches or which is intercepted by dA. Okay? So when a surface is going to emit radiation in all directions, the fraction which is intercepted or which reaches another surface, that is called the shape factor or view factor. So therefore, it has to lie between 0 and 1. We will see that later. But this shape factor is a very, very important concept. Okay. We will pick up from here on Wednesday morning. It's 10:56 now. But I just wanted to, let me stop sharing. Now, what I wanted to do is I also wanted to now announce the test, the first class test, first full-fledged 1 hour class test. You had one quiz already. So that first class test is going to be on Thursday night. Okay. Thursday night. Would 8 to 9 p.m. be okay? Or do you want it earlier, like 7:30 to 8:30, so that you are not late for dinner? Normally, when we are in campus, we do it from 8:30 to 9:30 because people can finish their dinner and then
Sir,
come.
you
Yeah.
mean this Thursday?
Yes.
Okay.
Okay. What would you like? 8 to 9, 7:30 to 8:30, 8:30 to 9:30. 8:30 to 9:30, I have a problem actually. Uh, it's okay. I mean, if not, some of the TAs would conduct it. Not a big deal. Okay. If there are, if if there is no preference, then I would keep it from 8 to 9. Is that okay?
Yes, sir.
Okay. 8 to 9, the format will be like this. Okay. It will be a 1 hour or maybe 45 minutes. I'll decide after I set the paper. This will be pen and paper. Okay. So I will upload the question paper and also email it to you right at the beginning of the exam. And what you have to do is you have to complete the paper, let us say within 45 minutes, and then you will have another 10 minutes to upload that. You have to scan your answer script and upload it on the shared drive. Again, the uploading will have to be, I'll give a format of the file name. Basically, it will be your roll number. Okay, so that's what you will have to do. And so make sure that your network, etc., are all okay. Only in the worst case, please keep this in mind. Only in the worst case, email it to me. If you are unable to upload, your drive is not accessible. Typically, it doesn't happen, but it happens to maybe some one or two times. Only
Sir,
then
can you repeat the uploading method? Sorry.
uploading will be in a Google shared drive. I will give you the link. You'll be able to, with your edit rights, you will be able to go and upload. Okay.
Sir, actually, the issue with giving editing rights is we can upload as well as remove stuff.
No, that I can see that. I can see that log. Okay.
Oh,
If,
okay.
if anybody does that, anybody deletes any, if anyone deletes any file, okay, the Google Drive, I'll be able to know who is doing it. Consequences will be very, very severe. It has not happened. Don't worry, Jaskar. It has not happened yet. Once one guy tried to do, and then I figured out he was actually deleting his own file. So because he was not sure whether his uploading was complete. Okay, but otherwise people don't do that, and you will have only a very short window. Okay, so it's like 10 minutes or so by which you have to upload. After which I will remove the editing rights. And anyway, in any case, if you right after that, make sure after 10 minutes, just make sure that your file is there. Once I've removed the editing rights, you will know. If you think that if you see that it is deleted, immediately send me an email. So there are ways. Don't worry about that. Nobody will be unfairly penalized because of some different acts by somebody else. Okay. All right. So let me stop the recording here, and I will stay here as usual for the next 4-5 minutes. If you have
Sir, what
questions.
will be the syllabus?
Okay. So let me keep that in the recording as well. Syllabus, as I said last week, is conduction heat transfer, which includes 1D, 2D, as well as transient. Okay. Now I can stop the recording. Okay, friends.